Okay, next we are going to solve the fifth one. The first four we have already solved, and in this one we have this 8 cycle, and we have to find the cycle structures of all the powers of this 8 cycle. That means the cycle structures of permutations which look like this, where m is any integer. So m can be negative also. We are going to see those things, but in the solution, first what we are going to do, we are going to calculate the first few positive powers and see what happens, and we will realize something, and from that realization we will be able to handle this general case. So let's see the solution. So we straight away start calculating the positive integral powers. Because we want to show all positive integral powers, that's why we are writing this one also, although it's trivial, you know that it is equal to the 8 cycle itself. So that itself is the cycle structure of the first power, then the second power. Now to calculate the second power, you just simply do what we have been doing all along. This square by definition is this product, and then you calculate the product, because in this text we are using this notation instead of this notation to denote the value of the function f at the input x. So that is why while calculating this product, we start from the left side and then move rightward. And you can understand why we are doing that, because these are after all functions, no? So we are considering this composition means our input x will be here. So that's why we will apply this one first, and then on that we are going to apply this. So that's why we start from this side. So first 1 is sent to 2 by this one, and this one will then send 2 to 3. So 1 goes to 3. Like that, 3 will be sent to 4 by this one, and this one will send 4 to 5. Then 5 to 6, 6 to 7. 7 to 8, 8 goes back to 1. So that means 7 comes back to 1. So that is one cycle, and then we proceed with 2. This one sends 2 to 3, and then that 3 is sent to 4 by this second one. So 2 goes to 4. 4 goes to 5, 5 goes to 6. 6 to 7, 7 to 8. 8 to 1. 1 to 2, so that means 8 comes back to 2. So this is the cycle structure of the second power. So we write like this: 1 3 5 7 times 2 4 6 8. And whenever we are calculating cycle structure, you already know that these are going to be disjoint cycles, which they are in this case. So next we calculate the higher powers. Then Q. So if you recall this calculation, we had to go like this. Now 2 steps we had to take. 1 to 2, 2 to 3. So 1 to 3. Here we will have to take 3 steps. So 1 to 2, 2 to 3, 3 to 4. So 1 to 4. 4 to 5, 5 to 6, 6 to 7. 7 to 8, 8 to 1, 1 to 2. Then 2 to 3, 3 to 4, 4 to 5. 5 to 6, 6 to 7, 7 to 8. 8 to 1, 1 to 2, 2 to 3. One more will be there. 3 to 4, 4 to 5, 5 to 6. And then we are still not done. We then have to see what happens to 6. 6 to 7, 7 to 8, 8 to 1. So that means 6 comes back to 1. So this third power is also an 8 cycle, a different 8 cycle than this one. Next, the fourth power. So here we will have to take 4 steps, but instead of doing like that, because it will get more and more difficult to do it like that. So what we do instead, we use the rules of exponents to write this as this times this, so that we can use the previous calculation. That means this we have already calculated, and it sends 1 to 4, and this one sends that 4 to 5. That means 1 goes to 5. Okay. This one sends 5 to 8, and this one takes 8 back to 1. So that means 5 goes back to 1. So we get 1 cycle. And then 2. 2 to 5, 5 to 6. 6 to 1, 1 to 2. So 6 goes back to 2. Another cycle we have got. Then 3. 3 to 6, 6 to 7. So 3 to 7. This one also will likely be a 2 cycle only. 7 to 2, 2 to 3. So 7 goes back to 3. Then what else is there? 4. 4 to 7 and 7 to 8. So that means 4 to 8. 8 to 3, and this one will send 3 back to 4. So 8 goes back to 4. So this is the cycle structure of the fourth power. You may be wondering how many of this we will have to calculate. We will see. Let us just keep on doing this. Here also we can apply that same technique. Write this as the fourth power times the 8 cycle. So that means here you can use this calculation. So the fourth power sends 1 to 5, and this one then will send, this one means only the 8 cycle will send that 5 to 6. So that means 1 goes to 6. Then 6 to 2, 2 to 3. So 6 goes to 3. 3 to 7, 7 to 8. So 3 goes to 8. Then 8 to 4, 4 to 5. 8 goes to 5. 5 to 1, 1 to 2. 5 to 2. 2 to 6, 6 to 7. 7 to 3, 3 to 4. And then 4 to 8, 8 to 1. So 4 goes back to 1. So this is again another 8 cycle, different from both this one as well as this one. Different I say because you see, this one maps 1 onto 2, This one maps 1 onto 4, this one maps 1 onto 6. So they are all distinct functions. Then the sixth power similarly 1 to 6, 6 to 7, 7 to 4, 4 to 5, 5 to 2, 2 to 3, 3 to 8, 8 to 1. Okay, so this one has become a single 4 cycle. So that means we will have another 4 cycle disjoint. We don't have 2 here, so let us start with 2. And again I am repeating, I have said this many times before, but again I am repeating, you can in fact start with any symbol here that has not appeared already. Okay, so we just simply choose to start with 2. If you want, you can start with 4 also, nothing will change. So 2 to 7, 7 to 8, that means 2 to 8. 8 to 5, 5 to 6. 6 to 3, 3 to 4. 4 to 1, 1 to 2. So 4 goes back to 2. So this is the cycle structure of the sixth power. Next, the seventh power. For the seventh power, we will start from this one, the previous one. 1 to 7, 7 to 8. 8 to 6, 6 to 7. 7 to 5, 5 to 6. 6 to 4, 4 to 5. 5 to 3, 3 to 4. 4 to 2, 2 to 3. 3 to 1, 1 to 2. And finally 2 to 8, 8 to 1. So that means 2 cycles back to 1. And what is the eighth power similarly if we calculate? 1 to 8, 8 to 1. So that means 1 goes to 1. Because we have been asked to find the cycle structure, so instead this will turn out to be the identity, but instead of writing E, we are going to actually write even the 1 cycles. 2 to 1, 1 to 2. So 2 to 2. 3 to 2, 2 to 3. 4 to 3, 3 to 4. 5 to 4, 4 to 5. Then 6 to 5, 5 to 6. 7 to 6, 6 to 7. And similarly you will see that you are getting 8 also. And this, of course, you understand that this is the identity. Okay, so you may now ask, fine, we have found the first 8 positive integral powers where all the exponents are positive. The first 8 positive integers are exponents. But we have been asked to find the cycle structure of all the powers of this. This is of course not all the powers, it's just only finitely, namely 8 of them. But there are infinitely many of them. So what can we do? Now we can in fact draw a very strong conclusion from these calculations. So let's see that now. The point to be noted here is that we have reached the identity, and that tells us something about the order of the cycle itself. You see, when we were considering all these powers starting from the first power, we did not get the identity till this stage. Only at this stage we are getting the identity. So what does that tell us? It tells us that this 8 cycle has order 8. So we can now draw our conclusion like this. The above, I think I already need ink. Give me a moment. The above calculations show that the order of this 8 cycle is equal to 8. Now from this we can in fact say something about the general power, and that something is this. You may have already guessed, but still the fact that this cycle has order 8 tells us that actually these are the only distinct powers that we will ever find. Thus, for any integer m, we will find integers q and r such that m is equal to 8q plus r, where r of course is satisfying these inequalities. Hence, so you understand what we did here. We have just divided m by 8. We have got the quotient q and remainder r by the Euclidean algorithm. Hence, if we now look at the power, the mth power of this, then that is equal to this 8q plus r, and now you use the rules of exponents that you have in any group. So this is equal to the 8th power of our 8 cycle times the rth power of this. But we have already seen that this becomes identity, so this part will vanish and we will be left with this. Now look at the values of r. R varies from 0 through 7. Okay. When you take r equal to 0, of course by definition you get the identity. and when you take the other values of r, you get the other powers for which we already calculated the cycle structure till this to the power 7. So the identity that we in fact got in that previous calculation by taking the 8th power, that case now comes from r equal to 0. So that case is also there. So that is why those powers are actually the only powers, and their cycle structures have already been found. So that means the cycle structures of all the powers of this 8 cycle have been found. So that's why the solution ends here. Next, exercise 6. Exercise 6 actually helps us develop a way of calculating the order of any permutation. So it has parts. The first one is, what is the order of an n cycle? Or B, what is the order of the product of disjoint cycles of lengths these lengths. And there is a part C also, which is the general one, which just simply asks how we can find the order of a general permutation. Part C is this: how do you find the order of a given permutation? Okay, so let's now see the solution. From the previous exercise, you may have already guessed that the order is going to be n. Just like in the previous one, we had an 8 cycle, its order turned out to be 8. So here also the order of a general n cycle is going to be n. But note that we cannot do that type of calculations now because n is general, so we don't really know what the possibilities are. So that means we have to argue generally. So let's see. Consider the n cycle if you want, you can also write 1, 2, 3, etc. all the way up to n. That in fact also denotes this itself, because you see, although it looks like a specific n cycle where you have 1, 2, 3, etc. But do not forget that in this section we are just simply writing the suffixes to get rid of the x's, which has been done to simplify the notation. But this 1 actually means x1, so this 1 is a general symbol in the set on which these permutations are acting. So if you want, you can write this also, but this is not just 1, 2, 3, etc. It's actually something general. Okay, and in fact the set S on which your permutations are acting, that need not contain numbers, that may have any objects whatsoever. We write only numbers to make our notations simply. But here, however, I have just simply decided to write general notation like this. Okay, so we consider the n cycle. Now what we are going to do, we are going to look at what the powers of this n cycle do to say x1, and that we are going to just simply mention what the result will be. Note that if I write like this, will you understand what it means? I don't have space here. Note that x1 xn to the power I is equal to xi plus 1 for okay, actually there is no need to consider the case I equal to 0, because you will realize why. When we are trying to calculate the order of some group element, we will consider only positive integral powers, now where the exponent is positive, so that's why it's enough to start with 1. Now what does this equation mean? You see, do not forget that this ith power of this n cycle is after all a permutation, and it is, that means it's a function. So you can apply this function on this symbol x1. Then what is the image? The image is xi plus 1. Here I have just simply mentioned what the thing is, but you can of course verify it. You can see that it, okay, this is true. For example, if you take I equal to 1, then you are just simply applying this n cycle on x1. And what does the n cycle do to x1? It sends x1 to x2. So you will have x2 here if you put I equal to 1. Similarly, if you take I equal to 2, then you will have to go 2 steps. So x1 to x2, then x2 to x3. So here the image will be x3, and that of course you are getting when you put I equal to 2 here. In general this is true, and you will say, we are just simply saying what will happen till the case I equal to n minus 1. Okay, now what conclusion can we draw from this? Thus, the conclusion that we draw from these equations, there is not a single equation. You change I, you get other equations. So from these equations, the conclusion that we draw is that none of these powers equals the identity. Thus, not equal to the identity but why? You see, had this power been the identity, it would have mapped x1 to x1, but that is not happening. You see, in all the for all the values of I here, what are the things that we are getting? When I is 1, the image is x2, x1 is sent to x2, when I is 2, it's x3. In fact, when you take the largest possible value here, I equal to n minus 1, you get xn, and x2, x3, x4, etc., xn, none of them equals x1 because they are distinct symbols. That means all these functions, they fail to fix x1. So it does not matter what they do to the other symbols, already it does not fix x, none of them fixes x1, so none of them can be the identity. So that conclusion we have drawn. Also, another thing that one can readily see from these equations itself, specifically from the equation which you obtain when you put I equal to n minus 1. In that case, the image is xn, but then if you take one more step, then you go back to x1, because then xn is mapped to x1 by another application of this cycle. So what we are saying is this: so unlike these other powers, this nth power does actually fix x1. But that's not, of course, enough to say that this nth power is the identity. It needs to fix the other symbols also. Okay. Now, since this n cycle can also be written like this: x2, x3, etc., xn, x1. Why is that so? That is because actually nothing has changed. I mean, when you think of it as of course they look different, but they are the same thing. x1 is mapped onto x2 by this one. This one also maps x1 to x2, and the other things also are just the same. So the thing here is that we have decided to start with x2, but we have maintained the cyclic structure. That's why the function has not changed. In fact, we mentioned this also. This is because a cycle does not change if we change the positions of the symbols in it. Maintaining the cyclic order. Okay, because of that we are having this. So that means whatever we did with the original n cycle, we can also do with this one, and we can draw a similar conclusion. We don't need this part, we need this one. because now this cycle, just like the original inside, they are the same thing but they look different. So similarly, exactly similarly, the nth power of this you can understand will map x2 to x2. These are the same thing, so the nth powers will also be the same thing. I mean, the nth power of this will be equal to this itself, but that, because of the way we have written it, just simply shows exactly similarly that that nth power will map x2 to x2. Since this, we similarly have, can I write similarly here? Simi I can write. We similarly have this. Okay, let us just show exactly how that is coming. This equal to this is a, okay, I needed to write this one first. x1, x2 and so on, xn, but that is also this xn, x1, and this is equal to x2. And now you can understand that we did this thing with x1 and x2, and the same thing is going to be true with the other symbols. In general, we have this. For all the variations of I. So that just simply means what? This nth power of the n cycle fixes all the xi's. And if we do have other additional symbols, they are also going to be fixed because they do not even make an appearance in this n cycle or in any power of it. Specifically this nth power, so they are also going to be going to stay fixed. They are not going to be changed by this nth power of the n cycle. So that means the nth power of the n cycle actually does not change anything, so it is the identity. Hence this is equal to the identity. So the previous positive integral powers, none of them equals the identity. So this is the first instance of having the identity. That is why the order of this n cycle is equal to n, and that's how we also have that special case. The order of that 8 cycle is equal to 8. This implies this is equal to n. So we have answered part A. Next, part B. Now we have k number of cycles and they are disjoint, and their lengths also I mean, we don't know. The lengths are also generally m1, m2 like that up to mk. We have to calculate next the order of their product. So let C1, C2, Ck be disjoint cycles of lengths, these lengths. The lengths are already given there in the exercise respectively. Now we know that disjoint cycles commute because they do not have any symbol in common. So whatever they do to the set of symbols, they do it locally. Where they have the symbols in them, they only do whatever they do in that part, and they do not interfere with the doings of the other disjoint cycles. Okay, so it does not matter which one you apply first, that is, they commute. Since I think I have already said this quite a few times about this specific thing, that why disjoint cycles commute, so I am not going to go into the detail once more. So I just simply write here, being disjoint the cycles commute. Okay. Now let M be a positive integer such that so we take the product of these disjoint cycles and consider the mth power of the product, and we also set that equal to identity. If this is something we have and we start from here, then what can we say? So m is that means some positive integral power of this product equals identity. Then the fact that these cycles are disjoint implies, and because of that, the fact that they are commuting, mutually commuting, that fact implies that this power is equal to this. And which in turn implies this next thing. Okay, now let us look at this final equation for a moment. You see, C1 is disjoint with all these cycles, so that means the symbols, whatever cycle it may be, I mean, we already know what its length is. Its length is m1. So it's an m1 cycle. So it will have some m1 symbols here. And its mth power, whatever that ultimately turns out to be, will also have these symbols only. Maybe permuted in some manner. We have already seen the calculation for the 8th cycle. Okay, just like that, those symbols will only appear, nothing else will appear here. However, on the other side, we similarly have the other cycles, and here also we have powers. It does not matter with, what m is, whether it is positive or negative. The symbols that will appear on the right hand side are all different from all the symbols appearing on the left hand side. So you can understand that as a function, the left hand side has the power to change only the symbols that are appearing here, whereas the right hand side has the power to change only the symbols that are appearing here. And this equation tells us that these two functions are equal. Okay, so will any one of them, actually the same function, have the power to change anything? No, because if it changes anything, I mean, see, they cannot change anything. So what I am trying to say here is that, for example, you concentrate on this symbol. This symbol is changed by this function, what you see on the right hand side. However, because this symbol does not appear here, this cannot change that same thing. Okay, I mean, the left hand side cannot change this symbol. However, they have to be equal. So the only option that we now have is that they must be identity. That means they actually do not change anything at all, because that is the only option we have. In that way only we can have equality. This changes whatever it changes, and this changes entirely different things. So if any one of them actually changes something, then there is a problem. You can never have equality. So that's why none of them actually changes anything. So both of them are equal to the identity. That is our next conclusion that we draw from this equation. And we are going to write the reason also like this. Since changes a symbol if and only if does not change it, the above equation implies that both of them must be equal to the identity. Thus, we get two things from this. One is this mth power of the first cycle equals the identity, and the other thing is this is equal to the identity, from which we get this. Ck to the power minus n. So this one we keep and run the same arguments with this equation. So we write, similarly, And we can do that because C2 is also having whatever symbols C2 has, they do not appear here, and that is the same with the other C's. Similarly, from this we have the mth power of C2 is also equal to identity. The mth power of C2 is also equal to identity and this. So now you understand how to proceed. Proceeding like this or continuing like this? We have the conclusion that the mth power of all the Ci's equal the identity. Okay. Hence, okay, so that means the mth power of all the Ci's are equal to the identity. And so what can we say from that? We already know that when this type of thing happens in a group, then the order of the element of which we are considering the power should divide the exponent m. So order of order of Ci, which is mi divides m for I varying from 1 through k. And where are we getting this thing from? This we are getting from part A, because Ci is an mi cycle, so its order is equal to mi. So this is where we are using part A, which of course we do not mention explicitly, it's understood. So now you have some positive, you see these are cycle lengths, right? All the mi's are cycle lengths, so they are, whatever the case is, they are all positive integers, and all of them are dividing this positive integer m. So by the definition of LCM, the LCM of all these mi's must divide m. Thus, or this implies this divides m, where this denotes the LCM of these mi's. If you are thinking why this weird notation, it is just an extension of the notation that Herstein has used in this book. Recall that for two integers, this is how Herstein denotes their greatest common divisor, and this is how he denotes their least common multiple. I haven't seen these notations anywhere outside this book, but because we are in this book itself, so we continue to use them, and so this is a natural extension of this notation. Okay. So that means, and what is this m? This m, recall, that is a positive integer such that the mth power of this product of these cycles, disjoint cycles, is equal to identity. If this happens, then the LCM of the lengths of these cycles divides m. Now in particular, there is a particular m for which also it will be true, and that particular m is just the order of that product. In particular, won't be able to write it here. This LCM divides the order of the product of these cycles. And why can we take this in place of m? That is simple. Because this thing is equal to identity. No, that is why. Okay. So this is something that we have found. Now we are going to find something opposite. But we also have now I am just going to write things directly. I will, however, explain how this equation is true. So we leave this conclusion, we let it rest, we are going to again use it. But now separately we also have this. Do you see why? What is this? This is the LCM of all the mi's. LCM is after all a common multiple. The least common multiple is fine, but we don't need the least part here. We just need the part which says that this integer, this positive integer, is a multiple of all the mi's. So that means this will be equal to something times mi. Let that something be, say, alpha I times mi for all I varying from 1 through k. Okay, so let me just show that justification here itself. So now with this information, if you calculate this power, what do you get then? do not forget that these are still disjoint cycles. So when you calculate one such power, it's the same as calculating the individual powers and taking their product. That is because the cycles all compute. So that means when we calculate this, we are actually calculating this. And if you continue this calculation, you can see that this thing is alpha 1 times m1, which after applying one of the rules of exponents becomes this. Just like that, the same thing is also alpha 2 m2 for some, all these alphas are some integers. m2 alpha 2 ck to the power mk alpha k, and these powers c1 to the power m1, c2 to the power m2 all the way up to ck to the power mk, they are all identity. Why? Because the exponents you see, they are cycle lengths, and we have already proved in part A that that is their order. These are their orders. So that's how this is equal to identity. But also we have this, hence just like before, the order of this base should divide the exponent. The order of the base divides the exponent. Now you combine these two divisibility relations, and also note that the numbers involved here are positive integers. Thus, they must be equal. This must be equal to this. So that is why when we have to calculate the order of a product of disjoint cycles, we take the LCM of their cycle lengths. That is the order, and this is why that is the order. And part C now is trivial. Part C asks us, so this is where part B ends, and part C just simply asks us to calculate the order of any permutation. Since, or let's just write like this, any permutation is a product of disjoint cycles. And once you get disjoint cycles, you can apply part B and part A actually also. So that's how you get the order of any given permutation to be equal to the LCM of the lengths of the cycles that are there in its cycle decomposition, and that completes the entire solution. So we just simply write now apply parts A and B. So you can see that this exercise and its solution is actually simply the theory that tells us how to calculate the order of a given permutation. So this is where things end, and let's just solve another one and then we will stop for tonight. Compute A inverse BA, where there are two parts. Part A has A equal to this one, this 3 cycle times this 2 cycle, and B equal to this 4 cycle 1, 5, 7, 9, and part B has A equal to this 3 cycle 5, 7, 9, and B also equal to this 3 cycle 1, 2, 3. So when we calculate A inverse BA, let's just put the values. Okay, now if you want to calculate A inverse, what will that be? It is the inverse of this product. That we already know is the product of the individual inverses but with the order reversed. The inverse of A will be inverse of 1, 2 times the inverse of this 3 cycle. That means inverse of 1, 2 is 1, 2 itself. Any 2 cycle is its own inverse. This is something we already know. And the inverse of 1, 3, 5 can be obtained by just changing the order. Changing the order means taking the absolute opposite order. We have 1, 3, 5. We write 5, 3, 1. Linearly, now do not think of any cyclic order or anything. Linearly, whatever you see, you just write its opposite. 1, 3, 5, 5, 3, 1. And the same is true for a cycle of any length. Times B. So B is 1, 5, 7, 9. Times A. 1, 3, 5, 1, 2. So let's now calculate. First 1 goes to 2, this one does not change to, this one does not change to, this one does not change to, this one changes to 1. So that means 1 goes to 1. So 1 is unchanged, it stays fixed. So it will not appear. Next 2. Is 2 going to be similar? 2 goes to 1, 1 goes to 5, then 5 goes to 7, and these two do not have 7. So that means 7 is where we stop. 2 goes to 7. So it's not like 1, it does change, it changes to 7. Then these two do not have 7, this one sends 7 to 9, and then we do not have 9. So 7 goes to 9. These two do not have 9, 9 goes to 1, then 1 goes to 3 and that's it. 9 goes to 3. Then this one does not have 3, this sends 3 to 1, then 1 is sent to 5 by this, then 5 is sent to 1 by this, and then that 1 changes to 2. So 3 goes back to 2. Now, is there anything else? 1 we have already seen, 1 does not change. 2, 3, 7, 9, 5 we haven't seen. Okay, so let us see 5. What happens to 5? 5, this one does not have 5, this one changes 5 to 3, and then this one does not have 3, and then that 3 goes back to 5. So 5 goes to 5, 5 is unchanged. So this is the answer. And then part B. Since here we do not even have to put the values or even look at them. That is because A and B are disjoint cycles, so they will commute. Since A and B are disjoint, they commute. Hence, A inverse BA. They commute means BA is equal to AB. So in this case, the answer is B, and that's just it. Do you notice one thing? This one, the second one, of course, is a trivial case. The first one is not trivial, and the thing to be noted here is that the cycle structure of B has not changed. B was a 4 cycle. Now A inverse BA is also a 4 cycle, and this in general is true. Elements of this type, which look like this, A inverse BA, they have the same cycle structure as the middle one, B, and this is a thing that will help us later on when we introduce a new equivalence relation on a group called conjugacy. Okay, then this fact, which we will prove in the next exercise, not today, in the next update, that will help us determine all the elements conjugate to a given permutation. And this is not just about a single cycle, it's true for any permutation. You have a permutation B, it has some cycle structure, then you form an element like this, A inverse BA, where A is any permutation. Then this has the original cycle structure that B has. Okay, and the converse is also true. If you have two permutations, say B and C, which have the same cycle structure, then you can find a permutation A for which C is equal to A inverse BA. Okay, so using this fact, we will be able to we will discuss about it later. Okay, so we will be able to find all the conjugacy classes in a permutation group, in a symmetric group. So let's end things here itself. If you want to say something about these things, you can write in the comment section below, or you can mail me at my usual address. It's there in the description. And the next video is on Friday. So we have done group theory today, so let's do field theory. Let's go back to field theory on Friday. So that's just it. I wrap up for tonight. So until the next update, this is me, Lucifer, from A Mathematical Room. Have a nice night.